So what do we mean by a potential divider? So a potential divider is typically two resistors. We've got R1 and R2, and the current will pass through both of these, and we know from Kirchhoff's first law the current will be the same all the way around. However, the voltage across each of the resistors, so V1 and V2, will depend on the size of the resistance. So something we've seen earlier on in this topic, the potential difference across each resistor is proportional to its resistance. So that's a really key idea. So if we looked at this worked example, so the Vs, the supply volts, is 20 volts, R1 is 3 ohms and R2 is 7 ohms. So we're asked to find the total current and then find V1 and V2. Okay, so the total current, I equals V over R. The total resistance is 3 plus 7, which is 10. So 20 divided by 10 is 2. So we have 2 amps around this circuit here. And then we know that V is equal to I times R, so I can calculate the voltage across R1, which is going to be 2 times 3, which is 6, and the voltage across R2, which is 2 times 7, that's going to be 14 volts. So, as we've mentioned here, this key idea, the voltage across each resistor is proportional to the value of resistance. So here we have 3 ohms and 7 ohms, so 6 volts and 14 volts. So in the same ratio, 3 to 7. So an alternative way of thinking about this is that V1 is the fraction of its resistance divided by the total, so 3 divided by 3 plus 7, which is 10. So 3/10 of the total, 20 volts, is 6. We can do the same for V2, so that's 7 divided by 10. So that fraction of the total is 14 volts. And we can see that it adds up to 20 volts. So this idea that the voltage is split according to the size of the resistance is a fundamental principle behind potential divider. So we can write a formula for V1 and then V2 in terms of these other terms, R1, R2 and Vs. So if we look at V1 here, we've said 3 over 10, which is R1 divided by R1 plus R2, multiplied by the total voltage, which is 20, and we're calling that Vs here. So R1 divided by R1 plus R2, this fraction of the resistance divided by the total, multiplied by the supply volts, will give me V1. And then V2 is basically the same, but rather than R1 on top, we can place R2. So this is called the potential divider formula or equation. It can be written in various different ways, but this is the one we're going to use in this lesson. So we can use this to work out the voltage across the 2 ohm resistor. So I'm trying to find V1, so we'll call this R1. Vs is 24, R1 is 2, R1 plus R2, 2 plus 6 is 8. 2 over 8 is a quarter, so a quarter of 24 is 6 volts. So we could have found this by working out the total resistance, and then the current, and then V equals I times R. And what we're actually doing here is combining all those 3 steps into one calculation. So you don't have to do it this way, but this is the recommended way of solving problems when we have potential dividers. Right, now it's your turn, so practice with these 2 questions. So rather than work out the total resistance, then the current, then V equals I times R, I want you to use the potential divider formula that we've just introduced to answer these 2 questions. So pause the video and then check your answers when you're ready. For question 1, we have some nice easy numbers, so we're going to use our potential divider formula. So we can call the 1 ohm resistor, we'll call that R1, and V1 is across it. So Vs, the supply volts, is 30. R1 is 1, R1 plus R2, 1 plus 5 is 6. So we want to find a sixth of the total volts, which is 5 volts. Then we can do the same for the 5 ohm resistor. Everything will be the same, but R1 should really be, well, we could call it V2 and R2, or we could just call it R1 again. It's entirely up to us. But in this case, it's going to be 5 divided by 6, so 5/6 of the total voltage, which is 25. So 2 key points here. So what do we notice about the answers? Well, they add up to 30, which is our understanding of voltage distributed in a series circuit. And also, perhaps more importantly, the voltage is in proportion to the resistance. So here we have a sixth of the total. So we have a sixth of the total voltage. And on here we have 5/6 of the total resistance. So we have 5/6 of the total voltage. Question 2, same idea, but now we've got some slightly less friendly numbers. So here I have 1.2 kilo ohms. So the way we've done this is we're using the potential divider formula. So the voltage across the resistor, VR, which is what we are told is 2.7 volts, is equal to the total voltage, 12, multiplied by the unknown resistance, R, divided by the total resistance, which would be R plus 1.2 kilo. And then if we rearrange this, so we've got R plus 1.2 kilo, take that from the bottom to the top, expand the brackets, and then just tidy that up, we should find we have a resistance of 348. So that would be the recommended way of doing it. Sometimes students find that a little bit complex and would rather use this approach, which is the more standard approach. So we could find the voltage across the 1.2 kilo. So it's going to be 12, take away 2.7, so that's 9.3 across here. Then because I know the voltage and I know the resistance, I can find the current. I equals V over R, which comes out at 7.75 milli. And then it's the same current all the way around, so R is equal to V over I. I know the voltage across the R resistor is 2.7, divided by the same current is 348. So sometimes students find this approach a little bit more straightforward. Either is fine. My recommendation would be to use this first approach, but if you're not that happy with the first approach, the second one is absolutely fine. Okay, N-type thermistors. We've mentioned these briefly before. This is the symbol, and this is a typical resistance temperature characteristic. So as the temperature increases, the resistance decreases. This would be for an N-type thermistor, which is what we normally mean at A-level when we talk about thermistors. There are P-type thermistors, which is a positive temperature coefficient, but generally speaking, we refer to N-type. So this is used a lot in temperature and heating control systems. So it's made from a semiconductor, and if we increase the temperature, then we release some of these electrons which were previously trapped in a valence band, and we can move those into the conduction band. So what we're saying is as the temperature increases, the number of free electrons increases. Therefore, for the same voltage, R equals V over I, we have a larger current, therefore the resistance goes down. LDRs, light-dependent resistors. This is our symbol, with or without the circle, that's optional. The basic shape is very similar. So as, in this case, the light intensity increases, the resistance goes down. So once again, it's a negative exponential relationship. It's also made of a semiconductor, not a siliconductor. It's made of silicon, which is a semiconductor. And the principle is similar to what we saw previously with the thermistor. So as the number of photons increases, because the light intensity increases, then more electrons are released from the previously trapped valence band, and we increase the number of delocalized electrons available. So the basic principle is very, very similar. Okay, so let's have a look at this worked example. So we have a fixed resistor, 12 kilo, we have an LDR, and we have a supply voltage of 9. So we're trying to find what is the potential difference across the LDR when we're in the dark. So we have a high resistance of the LDR, and it's of 6 mega ohms. So we can use our new formula. So the voltage across the LDR is equal to the supply volts, Vs, multiplied by the resistance of the LDR, divided by the total resistance. So we have 6 mega divided by 12 kilo plus 6 mega, and that's going to equal 8.98. So that shouldn't surprise us, because in the dark we have a high resistance, therefore most of the 9 volts, 8.98, is taken by the LDR. However, if we increase the light intensity and we reduce the resistance of the LDR to 1 kilo, then we can change 6 mega to 1 kilo. We can do the calculation again and we get 0.69. Again, that shouldn't surprise us. As the light intensity increases, the resistance of the LDR has decreased substantially. Therefore, the voltage that it will take of the 9 volts is reduced. And this idea of changing the voltage output, or the voltage across a particular component, as the resistance varies due to the conditions, is the fundamental principle behind potential divider circuits. Okay, let's look at a practical circuit. So I've got a series circuit. I've got my LDR, in this case without the circle, in series with a fixed resistor. How will we connect a night light, so a bulb, into this circuit so the bulb comes on when it gets dark? Okay, So we'd have to connect the bulb in parallel across the LDR. So why is that? So this would be our typical 3 or 4 mark answer if this was an exam question. So first of all, we need to say that as it gets dark, so as the light intensity drops, the resistance of the LDR increases. According to the potential divider formula, or our understanding of voltage in a series circuit, if the resistance of this section here increases, or the LDR increases, it will then take a larger share of the total volts. And because the bulb is connected in parallel, then they have the same voltage across each component. Therefore, the bulb will now turn on because the voltage across it is sufficient in order for the bulb to light. So that's our basic principle. So we're changing the distribution of the voltage depending on this variable resistance. Now, we could put a little caveat here. In actual fact, if this were a real circuit, a practical circuit, you might have some kind of additional amplification, so maybe a transistor or something else which is beyond the scope of physics A level. But the basic principle is as shown here. Right, 3 questions. Have a go at these, pause the video, and then press play when you're ready to check your answers. So question 1, very similar to the previous one, but in this case the fan will need to go across the resistor. So our answer would be as shown here, or the circuit will get 1 mark. So as the temperature increases, the resistance of the thermistor decreases. So the voltage share across the thermistor will go down, which means the voltage across the resistor will increase. And because the fan is connected in parallel, then its voltage will also increase and the fan will be turned on. Question 2 is about sensitivity. So we can see there's a steep gradient here and a shallow gradient here. So if we imagine this would be used for in an oven at 200 degrees C, then the temperature could vary significantly and there'll be very little variation in the resistance. So that would not be effective. However, if we use this in a fridge, then around about 4 degrees C, a small change either way would have a substantial difference in the resistance. Therefore, the voltage across the thermistor would change substantially, and we'd be able to measure that voltage change and then turn on the cooling system or turn off the cooling system as required. So the steeper the gradient, the greater the sensitivity of the thermistor or the LDR. Question 3, part A. So this would be our 2 marks. We have our potential divider circuit, R1 and R2, and then the LDR connected in parallel across R2. Okay, we need to work out the resistance of the parallel section. So we have 1 over 6,000 plus 1 over 12,000. Invert your answer. That gives us 4,000. Then we can use the potential divider formula to work out the voltage across our LDR parallel section, which is going to be 6 volts. In bright light, then the R1 doesn't change. The R2 doesn't change, but the resistance of the LDR will change. So again, we can work out the resistance of the parallel section is 1500, and then we can find the voltage across that parallel section, and it will change because the resistance of the LDR has changed. And part C is a recap of what we've mentioned previously. So as the light level decreases, the resistance of the LDR increases. Always be very clear about which component you're referring to. This causes the output voltage across the LDR to rise. Therefore, it takes a greater share of the supply volts. We could make reference to the potential divider formula. And then this change of voltage can be used to trigger or operate a switching mechanism. Right, a very quick recap. So these are the key ideas. You can read through those. Well done. So that is the end of potential dividers and the end of the electricity topic. Congratulations.